Well, good morning, everybody, and welcome to Ellensburg, Washington, USA. You're looking live at a title slide for today's talk, Nuclear Forensics at Pacific Northwest National Laboratory. The speaker today works at that establishment, Sean Scott, a chemist, as he identifies himself on the slide. Looks like we're 5 by 5. That's comforting to hear and to see. Let's get on camera here and we'll say hi to a number of you. Hi, everybody. Thank you for joining us today. If you're watching this in replay, the local time is 11:46 a.m. and Hannah Shamloo will start the introductions and announcements and things at noon. So I suppose our speaker will not begin until 20 minutes from now, probably. And if you're watching this in replay and you want to just fast forward to the next chapter title, that will be the beginning of Sean's talk today. But regardless, we're live with a bunch of folks, more than 130 so far, and more will pour in to watch this live stream. It's a live stream on YouTube. Can I say hi to a number of you before I turn the camera around and let you enjoy the room here? We have many guests from out of town today. Some came across Snoqualmie Pass. Springfield, Oregon, Newland, North Carolina, Webb Lake, Wisconsin, Lake Ozark, Missouri, Burlington, Washington, Oregon Central Coast, Garrett, the Dutch night owl from the Netherlands. Hello, Garrett. Chehalis, Washington. That's Jim. Bitterroot Valley, Montana. Barbara says hello from Indiana. Petersburg, Alaska. Burpengary, Australia. Dayton, Ohio. Fairbanks, Alaska. Central Washington University women's basketball defeated Western Washington University last night. Very satisfying. Greetings from snowy Missoula, Montana, says Stephen. Rob McGee, I believe Rob is down in Salem, Oregon. Vancouver, Washington. Hannah Shamloo is the boss. That's so true. Vancouver, Washington. Springfield, Illinois, and so on. So, thank you all for joining us. You've seen enough of my face if you've been watching the Cascades A to Z, so I think it's time to turn the camera around and let you enjoy the room. This is the Central Washington University Geology Department, and you're only seeing half the room because a bunch of folks want to stay off camera for personal reasons, whatever, that's fine. But you'll see the half of the room that have people who are officially fine with being on camera. So I hope you enjoyed today's lecture, Nuclear Forensics at Pacific Northwest National Laboratory. Thank you for joining us.
Well, I suppose that would tie it. But
Hey.
no, in the background.
No, this is weird, but you'll have to go in his office to see the petrified wood from Saddle Mountain that I put on a Ginkgo base too. Look at this first. Because that's one of Wes's, pictures. That's yours, by the way. All this is going to be yours.
Steve, thank you.
Now, look up in this corner here real close. That's that. He epoxies it on. But what he does, he takes a picture, he sets it on with little tweezers, takes a picture first, because after you glue it on, you'll see the glue mark, the epoxy will. And I had to polish. Remember that when I first showed it, it had a lot of the saw marks on it, from Carl's dad, Leroy. I had to take those out. And Wes, he's a perfectionist. I had to go back to his shop like 3-4 times up to the house, and then he looks at it, I can still see the scratches go down there. I spent 2 days over there. He came down the second day, and we kind of finished it with a diamond, some diamond paste on the leather wheel, and then I polished it up, finished up after that. But we got rid of all the scratches.
Steve, thank you.
This is identical, should be identical, off the same piece of log that he had for the other one. And just remember the big white one is the one that fits the inlays in there like that.
Wes Engstrom, if you see this, thank you. Thank you for this gift that Steve is giving us right now. Thank you, Wes.
He tries to see you on here. So.
Wow.
And then I think you got this earlier version, and Wes says he needs to update it because listening to all your lectures or whatever, he knows he's got stuff he needs to update or whatever. But you can have this one too. I think you have a copy. I don't know if you read it, but you can take this and you can give it to Hannah or something. I think Andrew's already got that. But and then you got the latest blues one from Carl and Wes. So
thank you, Steve.
now is your office going to be open after you leave here,
can
or
I just
you want
grab it? I'll just put it in the side room for now and just keep it nice and safe. Or would you rather just walk it down to my office?
Well, whatever. I kind of wanted Hannah to see it too here. She's down there. She got her head.
Hang on. Yep. Thank you.
You bet.
If you find me, I'll give you all these. That's true. I don't give all the answers. It's incentive though. If you see you, you're in a good spot. Yeah. Sometimes I do like to hang out at like a crux or something, and just let people linger around me. Hi, Nick.
Good luck today.
Thank you.
12:30?
12:30.
You're just going to bop out?
Yeah.
Okay. Be very curious.
Yeah,
what
me
happened.
too.
Did you see Alex D. from Washington Geological Survey?
I do now.
Yeah. He wondered if anything had happened since our last. I said, yes, I'm happy to report. So that thing he was talking about, if you remember, he had some project.
Yeah.
He said Tim's one of the PAs on the thing. Just talk to Tim.
I was going to go talk to Tim. What did I come to the conclusion of? I should have confirmed with him, but I think there was something I don't have that you need for this.
Okay. Well, let's see how today goes, and then otherwise.
Yeah.
Okay. Okay. Okay, I'm going to put one of these on our speaker, Sean, and I'll look at the iPad and we'll see if his audio is working properly. Okay, thank you. Okay, this is a hot mic, and we're going to test it on you. Can I just come right in here?
Yeah.
Right there. So, tell us about your morning, Sean, while I see if your audio worked. Who did you meet with first?
Well, I met with you.
Yeah.
That was the first thing. But well, I stopped at Vindman's Bakery, of course.
Okay.
I got myself a maple pecan bun.
Good.
Gobbled it up. Met with you. You know, it's a good morning. I drove up through. You can either drive along the Yakima River, basically, or along the Columbia. And today I chose the Columbia because on the way to Vantage, there's a lot of cliffs, big basalt cliffs, you know, and I thought it would be cool with the snow on it. So it was awesome.
Was it good?
Yeah, usually I come the Yakima way because there's usually less semi-trucks or more opportunities to pass them.
Right. Yes, exactly.
Yeah, but I thought the Vantage Way would be cool, so.
So how are you going to go back? You're going to take Yakima back, you think?
It's a good question. Depends on how I'm feeling at the end of the day. I guess if I'm really tired, maybe I'll take the Yakima rate. I love driving through the canyon.
Me too.
The Yakima River Canyon. It's pretty amazing.
Okay, Sean, see here? These guys can all hear you. These are in the live chat. Sean, 5 by 5 means loud and clear. So I think we're good.
Okay.
Okay.
Cool.
So we're going to get started in just a few minutes, but just be aware that anytime you chat with somebody, they can hear you now. Okay?
All right.
All right. Thanks, everybody.
Rock counting for you? So stressful. I don't do it. I don't know if I'm gonna.
A geology class?
Nick is trying to convince me here that he can be a great TA by providing the students a terrible experience.
See, and now what I'm saying is that doesn't make sense, but it makes sense to me, so I have to be a TA to show him how it makes sense.
It's his hook to convince Jordan to let him be a TA.
It's the writing hook.
But I'm not sure I'm hooked.
I think you need to workshop this a little more. I don't know.
You know, a great man once said everything's worth a shot.
You said that. Faith, anything for the live viewers right now?
Anything for the live viewers? I don't know. I don't think so.
What classes did you have this week? What classes
This
are you
week,
taking this
mineralogy with Chris.
Mineralogy.
Yeah, I'm really liking that.
Good.
I'm excited. And then I'm taking Hannah's isotopes next quarter, and I'm really excited for that. And then I have 202 with Walter and Audrey, and that's cool. And then I have a geography class, and it's not like, it's very interesting because it's Geography 101, and I took it because I'm a geologist who doesn't know where anything is. But it's not really about like names of places, it's more about like history and like the environment and the humans and like their relationship. So it's very like cerebral and philosophical and ecology, but it doesn't tell me what river's what.
That's why I switched from geography to geology. I got to tell you, I was a geography major once upon a time, and it was like, I don't think I'm learning anything
It's
tangible.
interesting.
Right.
You know, it helps me understand like current world issues.
Right.
But the rocks don't really care about that.
Exactly. Very good. Good job. Hey.
Sorry.
This clock is slow, so that clock's a couple minutes slow, so I think we're there.
It's time. Let's
So
ride, boys.
I'm going to turn on the mythical boom boom.
Were you able to take like a break?
Oh, yeah. Got to walk around a little bit.
Hello. It's good to see you.
Yeah.
Okay.
Yeah.
Can you help me?
only
I'm
10
going
of
to
them,
turn
but
this up
it's
slowly,
just like
and I just want to let you
a
know.
flyer on
give me some
nuclear
feedback
forensics.
on what you can hear here.
And this kind of talks about some of the stuff we're working on in the current initiative, and then that
Well, hello everybody.
QR code goes to the website.
We're testing
But, like, if you
boom boom
search for
here.
Canada
Testing.
Nuclear Forensics, it goes, you'll find it.
Are we amplified more?
Have your information for internships, or should I say anything about that?
Keep going up a little more.
Should.
Is there feedback right now, or is this feeling
I
okay?
mean, I know I've given my email to.
A little
Chris, but,
feedback?
like, I would say if there's someone that wants to,
Didn't make it.
yeah, or like
Thumbs up?
anyone can email me.
chat.
Yeah.
Sean speaking. Yeah, okay.
All right, we're going to get going here. Welcome to another Friday seminar. Good to see you all. I hope the snacks are to your liking. If you don't like the snacks, let me know, but my answer might be too bad. But I'm going to do my best with the snacks, so if you have a suggestion, let me know. Okay, a couple announcements. If you are in 304 or 504, make sure you're checking in with Tim Malborn, who has his hand up right there. Thank you, Tim. If you have not filled out a release form, make sure you're checking in with Bree McInnes in the back corner. Whether you are on camera sitting here or off camera sitting here, you still need to see Bree if you haven't done so already. We have 2 remaining talks in this series left. No talk next week. It's Valentine's Day. So we were intentional about taking a break. Or it just worked out that way. I don't know. So 2 talks left. They're both our own CWU faculty. So we have Ann Egger, February 21st, and then we have Paul Winberry, February 28th. Ann's talk will be about science education, and Paul will talk about his research in Antarctica. So that'll be interesting. Other announcements, I think that's it. Okay, allow me to introduce our speaker. So it's with great pleasure that I'm introducing Sean Scott here. Sean is a Washington native. He's from Seattle area. He did his bachelor's here at Central Washington. So he got a BS in geology when geology was still in Lynn Hall that way. So a little bit of a stranger to this building, but not a stranger to campus. He got his master's in geology at New Mexico State in Los Cruces, a PhD in geology at the University of Wyoming, and then was a scientist at the Public Health Lab at the University of Wisconsin-Madison. Since then, he's been working at the Pacific Northwest National Laboratory, PNNL, just an hour from here. If you did not get a chance to talk to Sean today about internships, and you want to talk to Sean about internships, feel free to come up and talk to him after his talk. Take a flyer. I'm going to put these flyers right here. But I think that's it. So he's going to walk us through what he's doing at the National Lab. So please help me welcome Sean Scott.
All right, well, yeah, thank you, Hannah, for that introduction. Very, very happy to be here. I, kind of got my start as a scientist here. I'm in the geology department, and every time I come back to Ellensburg, it feels like I'm coming home. It's a place where I have a lot of really good memories, and everything that I have now, all the things that I've done, really started here. So, yeah, today I'm here to talk about nuclear forensics at Pacific Northwest National Lab. If you don't know what that is, I'm going to help you define it, help you understand what that means. It's going to be kind of technical at times, but not always. And what I really am here to do is talk to students and talk to everyone about the need for certain skill sets. And those skill sets kind of involve things like mass spectrometry, radiation detection, chemistry. These are skill sets that you actually do learn in geology departments. And you should see some instruments here that look familiar to you as you've done your studies here. So just so you know, this is Field Camp 2009, Peck's Canyon in Idaho. There I am. There's Jeff Lee, the infamous Jeff Lee, who was our instructor at the time. And like Hannah said, all of my education in geology. And you can see a lot of happy faces there. We were having a very good time out there in the field. Throughout my time, I really got into isotopes very early on. Now, when I first started geology, the reason to me was pretty clear. There was a class here taught by Nick and Charlie Rubin down in the Owens Valley in California. It sounded like I got to do a lot of hiking, and that sounded pretty cool. And that's something that I grew up doing, and so it really interested me right away. Now, this picture here on the right, this is a Sector 54 thermal ionization mass spectrometer. This is the exact same instrument that I first learned to measure isotopes on. It was in Lind Hall in a little closet-y type of room. And I don't mean an instrument like this. It was this exact same one that was put in a U-Haul and shipped down to New Mexico State University, where I continued to use it as a master's student, the same instrument. These pictures here, as a geologist, I've gotten to go out and do all kinds of different things. I've poked hot lava in Hawaii. This was on a geology CWU field trip. Collected samples in Yellowstone. Looked at bacterial vents on the ocean floor. Many, many other things, all in geology. But all the time, to me, it always came back to looking at isotopes. And part of being a geologist and studying geology causes you to look at the world differently. And you have lots of different tools to do that, whether you're a structural geologist, sedimentology, geomorphology, whatever it is. For me, the tool of choice was the mass spectrometer. And so that's kind of led me on this journey through many different fields and into where I am now. So I want to kind of talk a little bit about the national labs and PNNL. So there are 17 national laboratories in the United States. They are all owned by the DOE, and some of them are under different offices. So there's NNSA labs, there's Office of Science labs, and other labs. PNNL up here, this is under the Office of Science. And you can see they're all over the country. So if you have interest even in living somewhere and you think you might be interested in some of the work that we do at the DOE and within the laboratory complex, you can look in all these different places. Savannah River, that's an interesting one. They had similar activities to what was done at PNNL decades ago. Oak Ridge, Los Alamos, Lawrence Livermore, all these different labs that you can explore, all the different things that they do, all these different types of science. So PNNL specifically, we have 4 different campuses. The main one is here in Richland. Ellensburg's right up there somewhere. So just a little ways away. It's near the Hanford site. And if you don't know, the Hanford site is where they produced plutonium during sort of beginning in World War II and onward. So there's a sort of a lot of history there associated with nuclear sciences. We have a campus in Seattle, a SQUIM campus. That's the Marine and Coastal Research Laboratory. And then some campuses. And then nowadays we have people all over the country working for PNNL doing hybrid and remote work. PNNL is kind of interesting in that it's very diverse in the types of science that we do. A lot of national security work, but energy and environment, that's things like environmental chemistry, environmental cleanup, especially at Hanford. Lots of different types of science, just generally biological sciences, battery storage sciences. I mean, the number of things we do is vast and more things than I know about for sure. And then these are just some statistics that are the most recent ones that I was able to pull. So an annual spending budget of $1.6 billion, lots of staff, peer-reviewed publications, invention disclosures. So we're a diverse lab, we do lots of different things, and it's getting to be pretty big. So I work in the National Security Directorate, and I was going to kind of talk a little bit about what we do. So national security is quite diverse, as you might imagine, lots of different things to address. A lot of what I'm going to be talking about today is sort of nuclear non-proliferation and the types of analytical chemistry techniques that we do. But there's lots of different things. So nuclear material processing, that's sort of more of like the legacy of Hanford, right? So, back in the day when we had all the reactors there irradiating fuels and making plutonium, a lot of the sort of legacy and history of those processes remain at PNNL, like the knowledge base that we're trying to maintain. Chemical and biological detection and forensics, you could think of this as chemicals of concern, drugs, things like fentanyl, trying to understand those distribution pathways. Down here, data sciences, like artificial intelligence, these things are huge right now. AI is, if I don't know how you wouldn't know about that, but lots of things going on in artificial intelligence, and there's a lot of national security concerns there. And then safeguards and policy engagement. So we do a lot of engagement with politicians and policymakers as well. So I'm going to sort of start just getting into what nuclear forensics is, and it's going to sort of increase in technicality until the end. But what I really think everyone should think about, especially students during this talk, is how some of these things that I'm going to be talking about, how they might relate to things that you've learned as a geologist and here in this department. And so basically, these are these 3 components that are really going to be the focus of this talk: analytical chemistry. So what is it? This here is basically the technical definition: characterization of interdicted materials or devices found outside of regulatory control and post-detonation nuclear events. So there's a boom, right? Before the boom, you have interdicted nuclear material. So that could be, uranium oxide, plutonium, whatever it is. A device, so that's something that contains nuclear material. And then obviously this boom here. And then once the device is detonated, what is the nature of that? And so essentially, we're doing this to assist law enforcement and intelligence agencies in preventing, mitigating, attributing a nuclear or radiological event. So it's really about trying to prevent these things from happening sort of globally. And the important thing is that it utilizes a multidisciplinary technical team. It's an incredibly multidisciplinary science, many different people with many different backgrounds working on this problem. This is sort of the flow for what we do at PNNL. So we do sort of the laboratory analysis component of this. And this is essentially this sort of circle of things, right? So samples are collected, something called sample screening, dissolutions, post-dissolution measurements, chemical separations, and isotopic measurements. And so I'm going to get into more details for some of these things. But the important thing is that in all of these sort of parts, there's a huge range of analytical techniques and skill sets that we need, and we have all of these things: geochemistry, analytical chemistry, radiochemistry. These are skills that we need to be able to make this process work. And sort of very, very importantly, and what's maybe perhaps the most different from geology is that you got to have a process that's flexible and rapid. When you get a sample, you need to be able to deal with it quickly, and you might not necessarily know what type of sample you're going to get until you get it. The other component is sort of the difference between operational work and R&D. So we have a team of people, a large team. It's maybe 50 people or so. And we have kind of these two components, right? So we have operations, and this means that this is the capability that we maintain for nuclear forensics in general, so what you might think of as an event. And then there's a lot of R&D. So operations, basically, this is the method, this is how we do it. It's under very strict quality control sort of regimen. And then there's R&D, so that's how do we make the process better, right? But that's not necessarily operational until we put a lot of effort into it. There are times when, during an event, things kind of get a little crazy, and anything, we do the operational work, but then anything that we're doing that's new, we can also implement and see if it can be incorporated into operations. And so there's sort of this overlap here during an event, and then sometimes maybe some of the R&D actually gets transitioned depending on how it performs. So there's kind of this daily work where you come in and you do your job, you maybe work your 8 to 5, whatever it is. During this time period, you might be working 24/7 with a team of people under a very sort of strict and intense environment. So what's maybe the most interesting thing to me, or something that really caught me when I first started working at PNNL, was what the lab looks like. And the lab looks a lot like a geology lab, so I snuck this picture in, because this is your guys' lab. Really the difference is you guys don't have these stickers on all your stuff, right? So we've got fume hoods, people doing separations. This is a germanium, high purity germanium detector. These are found in lots of geology departments. This is a thermal ionization mass spec. So just like the one I showed previously, a slightly newer version, an ICP OES. So these are the things. You walk into one of these labs, as a geologist, if you've been in a geology department that has a laboratory like this, you're going to walk in here and you're going to feel pretty comfortable. It's going to look familiar to you. So what are we trying to do? It's not just a bunch of laboratory analyses. What we're trying to do is we have an event and we're trying to understand the nature of whatever it was that caused the event. So like there's a device here. We're trying to do a bunch of measurements and sort of back calculate what the original device or item was. And some of the questions are these, right? Was there a nuclear yield? So you might have nuclear material in a device, but a nuclear yield is, was there fission? Was there an actual atomic event, or was it just dispersed nuclear material? Yeah, what was the design? Was it a US device, right? I mean, these are just basic questions that we're trying to understand based on chemical analyses. And then some of these are, the really important ones, right? Where were the materials produced? Was it a US material? And a lot of these analytical signatures allow us to answer those questions. And probably another important one, right, is there going to be another one? Yeah, I mean, it says at the bottom, it's any event with unknown radioactivity. We're just doing analytical chemistry, right? The analytes might be relatively unique or rare, but we're just going into the laboratory and we're doing analytical work that a lot of people do for lots of different reasons. So, yeah, things are going to get a little bit technical here, I think. So, like I was saying, analytical signatures, interpretation of a suite of analytical measurements. So there's prompt signals, things like satellites, and things like seismic. I'm sure people know what that means. And then isotopic measurements. So maybe one of the things that's important to understand is that we're not just analyzing elements. So we don't just want to know the concentration of uranium, right? We want to know the concentration of uranium-235, right? So all these measurements that we're doing are isotopic measurements. So this diagram here, this is what's called a fission yield curve, okay? So when uranium undergoes fission, it produces two new isotopes that are asymmetric in their masses. So that's basically what this curve is showing. So on the x-axis, you have mass number. On the y-axis, you have fission yield, okay? When uranium-235 is bombarded with different energies of neutrons, which are shown in these different colors, you get these yields of fission products. And then you have peak yield fission products, here where the peaks are. And then you have the valley in the middle and the wings. And the shape of this curve, exactly what this valley and what these wings look like, can tell you information about the incident neutron energies. And it's really important. Each one of these points is an individual measurement. And so you can imagine that we have to do a lot of measurements to construct this yield curve. And like I've said, nuclear forensics involves a lot of different things. PNL, we mostly focus on this part of it. But when there's a detonated device, there's going to be a number of different collections. So we might collect debris from the ground, debris from the air, something called prompt, which is basically your seismic and observables, things like that. And then this information gets passed on to additional people who do this stuff. So like I showed in that fission yield curve, we are looking at a huge range of mass. And so we're looking at almost the whole periodic table when we do these things. And so the challenge is, how do we measure individual isotopes of all these different elements that are relevant and needed to construct those yield curves? And what's really challenging about it is you might get a sample and it's really hard to collect that sample. Someone had to either fly a plane, someone had to go onto the ground in a radioactive environment and collect that sample. So the sample's precious and you really only have one chance. And you need to measure everything. So you get one sample, you need to measure a lot of different things, and you don't get a second chance at that sample. So everything has to go perfectly, which always happens. Sometimes you get multiple samples, sometimes you get multiple batches of samples. And you need to work quickly because a lot of the things you're measuring are radioactive and some of their half-lives are very short. So literally you're processing your sample and you're trying to get it analyzed as your analyte is disappearing. And most importantly, you have to have high confidence in the results because the results are used to make critical decisions, okay? If you're trying to attribute an event to a state or some actor, you need to be very confident in what you're doing because that's a pretty critical decision you're going to be making. It's like you get the sample, the thing's hot, it's radioactive, it's screaming hot. I mean, you put this thing next to it and it's just going off. So somebody has to be in there dealing with the sample. You're trying to measure all these isotopes. You need to recover them quantitatively, and you need to have these uncertainties. So whoever's working on these samples, like when we work with these samples, you have dosimeters, you have on the front of your body, you have a way to measure the radiation dose that you're receiving. You have rings on your fingers that measure radiation dose, and the DOE has limits on what you can absorb in a year. So it's just a very technically challenging environment, aside from the analytical challenges. So hopefully if you've taken a geochemistry class, you've seen something like this. This is just an excerpt of the table of nuclides. So all the stable isotopes are here, these black ones, the valley of stability, so it's called. The things we're looking at are not in that valley, right? We're looking at things that are radioactive, either here or here, that have been generated by fission and or activation. So like I said, fission products, activation products, and actinides. Fission, like I said before, that's when an atom splits. Okay? Activation is when an atom absorbs a neutron and becomes radioactive. So when I showed that fission yield curve, the mass range was from, let's say, 70 to 150 or something like that. But we also measure things far outside of that range, all the way from lithium, all the way up to americium. And so the actinides here, that's just this section of the periodic, it's kind of washed out, but uranium, neptunium, plutonium, americium. So one of the first things that we do when we get a sample is this thing called non-destructive gamma screening, which I'm going to talk a little bit more about later. But you basically take the thing and you put it in a gamma counter. This here is a track detector. This is one of our rad detection specialists, Bruce Pearson. So what this thing is sometimes the sample's, so the detector is actually here. Sometimes the sample's so hot that if you get it really close to the detector, it just saturates the detector. There's too much radiation. So you need it to be on this track so that you can move it away. So what we're trying to do here is measure peak yield fission products. So what we want to do is confirm the number of fissions that are on that sample. So we're trying to measure isotopes that are here up at the tops of these peaks, and that tells you the number of fissions that you have. And the gamma spectrometry, the way this works is that gamma rays are emitted during radiation that have specific energies, and so each one of these lines is associated with a specific isotope. And oftentimes isotopes have more than one line, so I'll talk about some of the things we do to address that. And so basically, when we want to do these analyses, we figure out the number of fissions. So let's say, whatever it's here. That way we can calculate the number of atoms we expect to have for all these different nuclides that we're required to measure. And I talked about half-lives and radioactivity before. So basically this kind of scale here is sort of like down here the half-life is long, up here the half-life is short. And so we kind of have to, you have to kind of figure out what isotope you're trying to measure, what its half-life is, what's the best way to measure it. So there's beta gamma emitters, alpha emitters, so that's going to kind of define what instrument you need to use. Down here, when the half-life gets really long, it's not really that efficient to use radiation detection, so that's when the mass spectrometry comes in. And there's going to be lots more about all of this. So when you think about on the previous slide, that was looking at half-lives, right? Now this is sort of the same scale, but looking at numbers of atoms. And so when the half-life is long, there tends to be a lot more atoms, right? When the half-life is short, by the time you get the sample and you're trying to measure it, there's not very many atoms left. And so that's sort of this line here. Okay, if you have 10 to the 5 atoms, you could probably measure it on a mass spectrometer. But it kind of depends, there's different considerations. So yeah, choosing how you want to analyze a sample. There's lots of different ways. So there's this idea of non-destructive bulk analysis. So that was what I was talking about with the gamma screening. So initially, before you do anything to the sample, you can take it, you can do some sort of analysis of that sample to try and understand its nature. How heterogeneous is it? What morphologies there are? This might even include something like SEM. You can kind of start to understand the basic elemental and isotopic composition of the bulk material. Is it a filter? Is it a soil? Things like that. Now the destructive bulk analysis, this is basically when you take a sample, maybe it's already a liquid, but you take a sample and you turn it into a liquid, and then you do a bunch of stuff after that, which I'm going to get into in fairly great detail. But in this way, sometimes this allows you to get better detection limits for a lot of the analytes and deal with interferences. And then, of course, there's microanalysis. So that's something like laser ablation, which you have here in this department. So just some of the techniques that I've mentioned already. So for the non-destructive bulk analysis, that's typically going to be gamma spectrometry. But when you get to the destructive analysis, there's a number of different options that you can use depending on the isotope properties, the half-lives, how many atoms you're going to get, and what's the mode of decay. Yeah, and so it's, just like what I just said. There's different types of decay. How are we going to use those things to choose the right method of analysis? Chemical separations in analysis. This is an ion exchange column. This is an anion resin, putting a nice green sample through there. This is something that you might do in a clean lab, something like the clean lab you have here. But why do we need to do that? So these are two diagrams of alpha spectra. So on the left, you're trying to measure what's called an alpha stipple. So you're trying to measure the alpha energy of a specific radionuclide, and you can see it's sort of this big, weird, broad peak. Whereas over here, kind of the same maximum energy right around there, but it's a really nice tight peak, okay? So what happens when an alpha particle when an atom decays and makes an alpha particle, the alpha particle is kind of large. So if you have a lot of matrix, if you have a lot of stuff in your sample, that alpha particle loses energy kind of randomly, right? So it spreads out the energy of that alpha particle by the time it gets to the detector. If you chemically purify that isotope and prepare it in a way that prevents it from having a lot of matrix interference, so in this case electrodeposition, you get a really, really nice peak that allows you to quantify the activity of that isotope more easily. And you can see also the difference in scale here. All these things that are getting spread out, they're all just right here, and the count rate goes way up, so you have much better detection limits as well. And the basic principle applies for mass spectrometry, any kind of spectrometry. If you can get a really clear, well-defined peak, you'll be able to quantify it more easily. So these are some of the things that we're going to go over. Dissolution, solution screening, sample splitting, spiking, elemental separations. So I'm going to kind of go into more detail about what all of these things are and how they look. So we might get a sample, a filter sample or something. That's sort of these examples here. So that's an air filter. You jam it into a beaker. You start adding what's called fuming nitric acid, and it starts reacting and it starts dissolving. And this process is pretty energetic and requires a lot of PPE, like shown there, and it's radioactive. So we have this process, the process of dissolution, working with radioactive samples and doing this dissolution takes an enormous amount of training, okay? So this is a skill that we need in this process that takes a long time to develop. As a geologist, I spent a lot of time doing digestions. I've dissolved many, many rocks, and it's really not that different, okay? It's a similar skill set. Once something's in solution, there's a number of ways that we screen that sample for the different things that we're trying to measure. So we take the solution and we put it in a gamma detector. So I didn't mention this before with the bulk analysis, but with gamma spectrometry, the geometry of the sample impacts the analysis. So when you do a gamma spectrometry scan of a filter, it's just sort of randomly, it's not randomly oriented, but it might not be in a perfectly calibrated geometry. So in this case, we can take a sample and we can put it in a vessel for which we've calibrated the efficiency of the instrument. So we get better peak yield fission product analysis this way. For the OES, the ICP OES, that's something where we take the sample and analyze it for its elemental composition. ICP-MS, this is something relatively new that we've added where we're able to do, in an unseparated sample, we're able to do ICP-MS analysis of the actinides. And I'll talk a little bit more about how we do that. And then, additional alpha activity measurements, and then this thing, KPA, for uranium concentration. So a lot of different ways we screen the solution. And this thing called splitting and spiking. So since we have so many analytes that we need to measure, we might take the original solution and separate it into several different solutions, and then we add things known as tracers. And so we can either add specific isotopes of the actinides, or we can add specific isotopes of other analytes of interest or stable tracers. And the way that we quantify the actual abundances of the isotopes really relies on this splitting and spiking and the tracer addition. So, like I said before, the ICP-MS screening of the actinides, that's one of the first things we do that gives us really important information. And this instrument here, this is an Agilent 8900. It's the same instrument that you guys have here in your department. Again, the only difference is this thing has had lots of radioactive material injected into it. So we take the sample, and we can actually, before we do any additional separations, we can take the dissolved sample, we can dilute it, and we can inject it right into the mass spectrometer. That's with all the fission products, activation products, and actinides. All the chemistry of that sample go into the mass spectrometer. And the chemical separation still matters, okay? So this is a diagram of the internal workings of that mass spectrometer. So we have an ion source. The sample gets nebulized and injected and makes ions here, okay? Then the ions enter what's called a quadrupole mass filter. That quadrupole mass filter can filter to a single AMU. Now, what you get, though, you still get interferences, isobaric interferences. So when it comes to plutonium and uranium, plutonium-239 and uranium-238 plus a hydrogen, that's 239 AMU. So it's the same mass. And the mass spectrometer can't tell the difference between those two things. It can only measure mass-to-charge ratio. So what we do is we add different types of gases into what's called the collision cell. And in this case, we use nitric oxide. And the nitric oxide reacts with the uranium and plutonium. And this is what's known as an online gas phase separation. So instead of doing a separation in wet chemistry using a column, you can use online gas phase separations. So in this example, plutonium reacts with the NO, and it makes an oxide, plutonium-239 plus 16 oxygen. Uranium has a different reactivity, and it makes a dioxide. So this is now 255 AMU, and this is now, what is that, 270 something. So plutonium, then you can use this second quadrupole mass filter that can filter to 1 AMU. Plutonium, you set it to that mass, it goes through, uranium dioxide is ejected. And so you can now measure your plutonium free of any interferences from uranium. And this type of technology is exploited very frequently in our laboratory using all different types of gases. And so this is just one example, right? But this is chemical separations, online chemical separations. So another thing that we do that we've been putting a lot of effort into is multi-collector ICP-MS. So this is an instrument it's like the one you have here, but it's just bigger, and it's a magnetic sector, and it has more than one detector. So in this case, while this instrument it has a collision cell and it can still do online gas phase separations, its introduction system is not quite as robust as the smaller instrument. And so we still do some chemical separations prior to analysis of the actinides. So in this example, we take our solution, we pass it through this series of columns called Utiva DGA. So this is basically a way to separate the actinides from each other. And then we get individual solutions of uranium, neptunium, plutonium, and americium. And we can inject them into the mass spectrometer to measure their isotopic ratios. And this is a diagram of that. So this is sort of the inner workings of this mass spectrometer. This is a relatively new type of technology. So prior to about maybe 5 years ago, the mass spectrometer would have started here with an ICP source. So this would have been over here. And you just send your ions through this double focusing mass spectrometer, magnetic sector, and then you can measure individual beams simultaneously on the multi-detection system. What we have now, so this is called a Neoma. It's made by Thermo Fisher. It has a collision cell, just like the Agilent 8900. And instead of a quadrupole in front of the collision cell, it has what's called this double wind filter. and you can filter out some ion beams, but it does not have 1 AMU resolution. So that's why in many ways we still need to separate some of the actinides. The important thing that this thing does is it filters out the argon beam that's used to generate the plasma. And so we get very nice peak shapes from that. So it does have some filtering capabilities that come in handy. Now, some of the R&D we're doing is using this instrument for online gas phase separations. So if we do have something like uranium and plutonium in the same sample, we can send uranium and plutonium through this filter, add CO2 gas into the collision cell. Uranium reacts to a monoxide and plutonium does not react. It stays as a plutonium metal ion. Those get sent through the double focusing part of the mass spec. They get separated in the magnetic field. And then we use the multi-detection part to measure both the plutonium and the uranium isotopes simultaneously. And that's what's shown. This is just a blow-up diagram of what the collector array looks like. And so we have uranium isotopes going into these Faraday cups, and then plutonium isotopes going into these ion counters. Now, Faraday cups, ion counters, they're just two different types of detectors, right? Faraday cup is used for large ion beams. Ion counters are used for small ion beams. And so the reason for doing this is because usually plutonium has a lot lower abundance than uranium by often several orders of magnitude. So you want your plutonium isotopes to be going onto the ion counters that can measure the smaller beams. So that's why we're doing this separation in this way. We're making uranium heavier than plutonium. Usually uranium would be on the lower mass side of this, and then we don't have any detectors down there. Now most of the ICP-MS work, we are working on operationalizing those methods, but right now they're still mostly R&D. So like I showed earlier in the talk, we have times when we have an event, our R&D and our operations combine. Now this method here, this is sort of what you might consider to be the traditional gold standard method for actinide isotopic analysis. And involves a fairly robust series of steps to get relatively pure actinides. And so it's a lot more chemistry, a lot more labor intensive, and it takes a lot more time to do it. But this is essentially considered the highest precision data. So this is, if you look at what people say about this, this is the gold standard, and this is thermal ionization mass spectrometry. So the first mass spectrometer I showed, the old VG Sector 54, that's what that is, a thermal ionization mass spec. So you actually have a purified sample of uranium or plutonium, and you actually load it in a little tiny droplet on a filament, and you put that filament under vacuum and you run a current through that filament and you make ions. Those ions get sent through just a single focusing, a magnetic sector, and then you can collect them on multiple cups. And this is our operational method, is using the TIMS, specifically a Triton, which is a thermo instrument. Now, when we move away from the actinides and we start getting into all those fission products and activation products, the chemistry gets extremely complex. So this is a flow sheet of how one might extract all these different elements from a single sample. Now, so we want to measure a single isotope of cadmium, a single isotope of gadmium, all these things that are radioactive. We know a path to get there, right? You go through this column and this column. And so this is just a very complex array of processes that we use to isolate all these different elements. And this is kind of where the tracers come in, right? This is just another example. So this is kind of what the columns look like. This is just a different method. So you might put this sample through a series of columns to get to some of these elements: gold, zinc, palladium, platinum, tungsten. So like I said, the tracers. This is really important for yielding, okay? So you want to know how much of an isotope was in an original sample. When you put the sample through that chemistry process, you are likely going to lose a small amount of it. Some of it's just going to be lost. Now, the people that do this stuff are really good, but you still need to know the chemical yield because it's not always perfect. So there are different techniques. Basically the same techniques, though, the same analytical techniques. You're either using a mass spec, an OES, different types of radiation detection. It depends on the tracer that you've added and its properties. And then some of these measurements. So the measurements are, we're trying to get back to what was originally in the sample. And so these measurements are done, the actual analytical chemistry is done on these things. This is an array of gamma detectors, more mass spectrometers. And then this is, we'll sort of go through some of these. So when we want to look at short-lived actinides, so these are things that, like I said before, sometimes their half-lives are too short and they have too few atoms to be amenable to measuring on a mass spectrometer, but we still want to know their concentrations. So if we want to measure, let's say, plutonium-236, we're going to spike that sample with plutonium-242, take it through a process, and since we know how much plutonium-242 we added, we can see at the end how much we have, and that is going to give us our chemical yield. And we're going to do that for a lot of the short-lived actinides, and they're most of the time alpha-emitting isotopes. So for some of these other fission products, so for strontium, for example, instead of adding a radioactive tracer, we add a stable tracer. So we add strontium, just regular strontium, to the sample. We know how much we added, and in the end, we can measure the amount that's left by OES. So that's a method where we're using non-rad detection to determine a chemical yield. For the peak yield fission products, that's when we do the analysis of the dissolved solution without going through any purifications, and that's where we get the really important peak yield fission products, moly-99, barium-140. So we haven't really, all we've done is dissolve the sample, so there's no need for a chemical yield tracer in that example. And then some of these other things, it really just depends. So silver-111, that's another fission product that we want to measure. We add a radioactive tracer, silver-110M, and we measure it by gamma spectrometry after all the chemistry to determine the yield. Terbium-161, that's more like strontium, where we're adding stable terbium and analyzing it by OES. Same with iron, so these are activation products, so these are not within the peak fission yield curve. These are just outside, but they are activated in the process. And then, yeah, some of these other things, short-lived actinides. So those are the ones that we did by alpha, and then these ones done by gamma, or this is the KPA. So it really just depends on the isotope properties. Sometimes we do isotope dilution mass spec. So that's what the gold standard with the thermal ionization mass spectrometry, which is what this is showing here. This is the wheel that holds all the filaments being loaded into the source. So we have different isotopic spikes that we add to the sample. And then our goal is to measure the isotopic compositions of all these different uranium and plutonium and neptunium isotopes and americium as well. And so we add these stable tracers to do an isotope dilution calculation at the end, which is similar to doing a chemical yield. So there's a lot of calculations that go into this, and maybe it would horrify you to learn that it's all done in Excel. The thing about Excel and trying to do data reduction using other methods like codes, like Python or something, Excel, you can trace it very, very easily. So anyone can go in here, you know, if you've set up your spreadsheets correctly, you enter in a value, an analytical value, and it goes through a series of calculations and data reductions. And if someone wants to go in there and say audit that process or audit that data reduction, they can go in there and it's easy for them to understand and see the calculations and where they're linked to. That's not always the case with some other types of data reduction where maybe someone has developed their own data reduction code, and then it's hard for another person to go in there and really understand it without diving into the code itself. And so it's just sort of the state of things, and Excel probably isn't that bad compared to doing it by hand. It's some way to track how all of these things are getting calculated. So this is an example. So we have an ongoing relationship with Washington State University, and they have a reactor and they do irradiations for us. This is a boron carbide vessel. And so basically, this is an example where they put some highly enriched uranium into a boron carbide vessel and irradiated it with different energies of neutrons. And you can see what happens. For high energy neutrons, the fission yield curve is different than for these different energies of neutrons. So again, this is that fission yield curve, and then the fission yield. So the calculations really aren't that complex. And this is just an example of how we get from start to finish. So basically, we have this tracer, silver 110M. We know its concentration. We add a certain amount of it to a sample, and so we know how much tracer activity we've added. Okay, pretty simple. We measure it at the end. You can see we have a little bit less than what we started with. You divide by the amount that you started with, and then you get a chemical yield. So this just tells you how much of this tracer has been carried through the process. Now we want to know how much silver 111, that's our target analyte. So this is what we measured. We divide by the chemical yield, and this is going to give us the activity in the original sample with all these errors being propagated throughout. We take the activity, divide by the decay constant, so that's activity equals number of atoms times lambda, the decay constant. So you just rearrange that. You get the number of atoms. So we know previously we've measured the number of atoms of Moly-99, kind of using the same principle. We know, based on nuclear data, what the fission yield is. We calculate the total number of fissions. So we look at the atoms measured from here, divide by the total number of fissions, and then we get the fission yield. So, you know, there's not a lot of complex math going on here. The things that are really complex are, you know, when you actually get data off of your detector, the actual data reduction to get to this number, that's where a lot of the complexity comes in. But actually getting to this final value that you're trying to report is really pretty simple math. And so a lot of the times we're comparing, you know, what we measure as a fission yield compared to other types of fissions that have been, you know, other types of irradiations, things like that. So in this example, this is the fission yield from boron carbide. So this is just regular natural boron and carbon. This is with no boron carbide shield. And then this is when you have boron 10. So this is an isotopically purified boron. So you can see the fission yields are a little bit different depending on the conditions. Now this is just another one. So this is when we do it by OES. And so you add a certain amount of stable samarium. You're trying to get to samarium 153. So you know how much you add. You measure the original concentration. And then you kind of do all those same set of calculations to determine how many atoms of samarium 153 you have, which this doesn't go through the whole calculation, but it's basically the same. The only difference is the chemical yield is measured by OES, right? So you're taking just a concentration of a stable amount of samarium and measuring it by OES. So there's a lot of different things that we're doing, a lot of different analyses, but the skills that we're using to do these things are common skills that you learn in a lot of different fields. But what you should really take away is that this is a multidisciplinary field. You have people who know radiation detection, you have physicists, you have chemists, nuclear engineers, geologists. The nuclear forensic process, it involves a number of things. Like I just said, all these dissolutions, rad detection, chemistry, mass spectrometry, even the logistics of collecting the sample and even dealing with it, even receiving the sample because it's radioactive. That's a whole process in and of itself. And definitely for the students here and for all the geologists around, you know, especially when it comes to the mass spectrometry, there's a lot of geologists. Most, you know, greater than 50% of the people I work with on mass spectrometry are geologists. And, you know, as far as doing all this other stuff, all the separations, rad detection, dissolutions, a lot of physicists and chemists. But these are things that we do in geology. And in the field of nuclear forensics in general, we need a workforce. We need people that know how to do this stuff. And one of the things that it suffers from is that people, for one, they might not even know that it exists. So that's one of the reasons why I'm here. But two, a lot of people, they come in and, we have attrition, and we need to maintain this workforce. And so if you're a geologist and you are familiar with these things and you have these skills, this might be something to look into, because this is something that we need for our national security globally. And I guess I will just leave it there. And happy to be here. Thanks for having me.
Thank you, Sean. Questions for Sean? And Sean will repeat the question for our home crowd watching live. Questions?
Back there.
Can you tell us a little bit about your journey from the geology bachelor's degree to how you went through your master's and PhD and around with it?
Oh yeah, sure. Okay, so the question was, what was my journey from a bachelor's degree to where I am now?
Thank you.
That's a really good question. I mean, it's really interesting looking back on it. Like I said, I got into geology because I was really interested in hiking and going outside and looking at rocks. And this department, and Nick in particular, and Charlie Rubin, and Jeff Lee, and everyone, they were all so enthusiastic. When we went down to Bishop, so I've also did a lot of music growing up, and so when we went down to Bishop, and you had that book of all the songs, and we have these jam sessions every night, and everyone's singing and having a good time. I mean, I really felt like that this was the thing for me, right? So also in the geology department, so once I really got into geology and felt really at home, there was this other aspect of isotopes. And there was a guy here whose name was Frank Ramos, who is now a professor at NMSU. And one of the first things he told me was that if you study isotopes and learn the fundamental aspects of isotope geochemistry and the analysis of isotopes, you'll be able to apply that to anything. Like, you can go study whatever you want, almost. There's really not a lot of limits. And that really resonated with me. And so after finishing my bachelor's degree here, I went and did my master's degree down with him at NMSU, where I worked on that old mass spectrometer, that old Sector 54 TIMS. And so down there, I started working on mid-ocean ridge basalts. I worked on opals from hydrothermal systems in southern New Mexico. I started getting into all different kinds of things, like studying, and to me it was really about, I'm out in the world walking around and I see a rock, and I'm like, I need to know the strontium isotope ratio of that rock. I need to know. And so it was really just allowing me, like isotopes was a tool that I really resonated with, that allowed me to investigate the things that caught my eye. Just like as a geologist, you see things all the time and you learn to see the world in a different way, right? In a way that, kind of transcends time. And so then during my PhD, so I went and worked for Ken Sims, who was a volcanologist, and there was a video of him going into Nyiragongo, which has an active lava lake in it, and he had his heat suit on, and he walked right up to the lava lake and just grabbed a sample right out of there. And that was pretty amazing, and I was like, wow, I want to work for that guy. And so went up there, and he happened to have a relatively new mass spectrometer, an ICP-MS, and he was also really supportive of me just kind of learning how to use it and analyzing all kinds of things, whatever I wanted. We'd be out in the field in Yellowstone, and he'd be like, what's the iron isotope ratio of that thing over there? And I'm like, oh, well, why don't we measure it? And so the whole time, I've always been doing all these isotopes while also getting to go out and hike and collect rocks and go on field trips, which was also personally rewarding to me. It's what I would do for fun anyways. And then I went to Wisconsin Public Health Lab, and I kind of took those principles of, you can use isotopes to study anything you want. And I just went really crazy there, right? I was grabbing animals and analyzing their femur bones and their livers and stuff like that. Analyzing plants, food, urine, like whatever you got, I will analyze it for whatever isotope you want me to. And so I got to like work on all different kinds of isotope systems, and I, again, had a mass spectrometer there that I had a lot of support for just doing those kinds of things and trying to develop things that would be impactful to public health. One of them that was really impactful was looking at lead isotopes in human blood. So there are a lot of kids still in the United States that get blood lead poisoning. And you can use lead isotopes to trace the sources of the lead that's in a person's blood. And so we got to work on several cases where they were difficult cases, where a lot of times the child is in an environment where it's very easy to figure out, you're like, okay, obviously this child's eating paint chips, like, stop them from doing that. But there are other times when there's no obvious thing going on, but their blood lead is elevated. And so we were starting to see, so they go into the house and they collect things. This is all, everyone was agreeing to it. And we started to see things like, oh, this person bought this spice overseas and that spice is contaminated with lead, right? And so you get to start that was really impactful to me because you got to see, you got to help a child lower their blood lead level. The family was happy, the health department's happy, everyone's happy, right? So you're really starting to make an impact. And the whole, it's the same techniques, though, that I use in geology. And of course, the whole time I'm out collecting water and rocks and doing all the other things I like to do. Now, coming to PNNL, it was just, again, they had a job opening for a chemist, right? And they had this brand new mass spectrometer that I showed, the Neoma. And I had known about the Neoma, and I was like, I want to get one of those. And I just had this opportunity, right? And you come and you just apply the same basic principles that I've learned the whole time to a new problem. And so it keeps you really engaged. Every time you're working on something new, you just sort of expand your mind. And that's what geology has always been to me. Just like expanding your mind, doing new things, seeing the world in a different way. So.
One more?
Chris?
Sean, I was just wondering if you can comment anything that's kind of on your radar screen, up and coming, that you're particularly excited about, either kind of on the analytical side or application side, that you've had a chance to be involved in.
What's the question, Sean?
Oh, sorry. Okay, so up and coming things that I'm excited about. I don't know. I don't think this is controversial, but so there's kind of been a renaissance in nuclear energy, right? And so there's a lot of interest in nuclear energy right now. A lot of the designs of new reactors require certain types of materials that people are still figuring out how to make. And so analytically, a lot of these things, we don't even know how to analyze them and get accurate data. Some of these things like salts, a lot of salts, different things with unusual isotopic ratios. I've been doing work with some in that field, and that's it's really cool to be sort of in on the beginning of it. So some of these advanced reactor designs that have been theorized and designed, again, I'm just using the same techniques I've learned all these years to do something new, and so I've been excited about that for sure. Yeah. I think maybe.
This is sort of related, but I wondered, what are the drivers of the R&D that you get to do? Do you get to follow your own, design what you want to do, or somebody say, we need to know about this thing?
Yeah, it's a little bit of both. So with ICP-MS, for example, like I was saying, the traditional operational method is thermal ionization mass spectrometry. And they're like, well, it's great. It gives us this really great data, but it's kind of slow. So we want something that's a little bit faster. So we know, let's look at ICP-MS. And that's about as much constrained as it is. They're like, well, we have these instruments that we think are faster. You over here, you know how to run this thing, and here's the problem. Figure out how to address it. And so it is, there's definitely sort of scope where you're like, okay, we want to make improvements to this process and we want to use this method, and that's about as much as you get. And then they're like, it's up to you, the technical person, the person who we've hired to, be the expert in this. It's up to you to make it happen. And so, and you kind of do have a lot of flexibility in exactly what direction you want to go in that regard, sort of understanding the end of where you want to be. Yeah.
Here, let's thank Sean one more time. Thank you, Hannah, for setting this up. See you all in 2 weeks, right? No lecture next Friday. We'll see you in 2 weeks. Goodbye. Good job.
Thanks. Yeah, hopefully, it's feeling like it was really technical there in the sort of middle of that.
This was perfect. It was perfect.
Especially in Wyoming.
Okay, everybody. Well, thank you very much for joining us today. Programming note that we will not see you next Friday at noon. That's Valentine's Day. It's also a 3-day weekend here in the United States. But 2 weeks from today, we will be doing a science education talk by Dr. Ann Egger from CWU. And 3 weeks from today, we will be doing an Antarctic geophysics talk by Paul Winberry, also from CWU. Okay? For some of you who are regular and deeply into the Cascades A to Z, I guess I need to start figuring out what we're going to do tomorrow morning at 8 a.m. Episode U, entitled Hammond Land. I'll see some of you tomorrow morning live, 8 a.m. Pacific time.
Let's see.
Saturday, February 8th of 2025. Thank you, everybody. I love you, and goodbye from Ellensburg, Washington, USA.